Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're doing a problem with the frictionless piston device that reaches the stops. It's not the first time we do this problem, right? We've done this problem at least 2 or 3 times already in the channel. You guys can check out the videos there. The gist of it is the same, yet there are slight differences on this one. So I'm not going to spend too much time explaining how this system works. We've done that in the past. You can check on the videos if you wish. I'll try to be a bit faster here. Okay, this is a problem by UNSW, and the problem statement reads like so. 5 kilograms of water at 15 degrees Celsius is contained in a vertical cylinder by a frictionless piston of a mass such that the pressure is 700 kilopascals. Heat is added slowly to the water, causing the piston to rise until it reaches a stop, at which point the volume inside the cylinder is 0.5 meters cubed. More heat is then transferred to the water until only saturated vapor exists. A. Find the final pressure in the cylinder, the heat transferred, and the work done during the process. And B. Show this on a TS diagram. Okay, so a couple of things to note in the beginning. We're, dealing with the vertical cylinder that is frictionless. And this frictionless means that all the energy that's going to be used to move this piston is coming from the fluid itself, in this case here, from the heat being given to this system. And this heat is not being, the energy given by this heat is not being lost in the form of friction. All of it's being used by the water. What else? This heat is slowly added. What does that mean? Well, slowly added means that this happens in a quasi-equilibrium manner, such that the pressure is always 700 kilopascals. And again, if you're in doubt, check the previous videos. Okay. What else? Note that we have a total of 3 states, because we first add heat. Okay, and then, where's the then? And then we add more heat afterwards. So we add heat until, so that this piston here is able to move, and it rises until it hits the stops. From that point onwards, it cannot move anymore. So therefore, the next addition of heat will cause the pressure to increase, but not the volume to change. Okay, that means that we start with a process. We start with a first state, and let's call this state number 1. Go ahead and call this state number 1. And then because of the quasi-equilibrium situation, after the heat is added, we end up with a situation that's also at the same pressure. So this can be considered an isobaric process. So that gives us number 2. Number 2, we know the volume becomes 0.5. We know the pressure. We know 2 things. The mass does not change, and the volume from this point onwards cannot change anymore because of these stops. So as we add more heat to the system, the volume cannot change. So as we get to state number 3, this is an isobaric process, so therefore the volume needs to be kept at 0.5. Okay, so that means that specific volume 2 needs to be the same as specific volume 3, because no mass or volume have changed, or no mass has entered or left the system, and the volume has not changed. What do we need to do? We need to find the final pressure. So in this case, pressure number 3, the total heat transfer, so Q total, which is going to be Q from 1 to 2 plus Q from 2 to 3, and work done. So work total, which in this case will be work from 1 to 2 plus work from 2 to 3. Right off the bat, I can tell you guys that work from 2 to 3 is nil, right? Nil. Why? Because there's no change in volume. So right off the bat, I can tell you this is 0, and work total is going to be just equal to work from 1 to 2. Okay. By the way, if I want to calculate work from 1 to 2, all I need to do is PdV. I need to grab difference in volume. I know the pressure already is 700. Okay. So let's go ahead and define all these states, grab properties for all of them, specifically internal energy, which I will use to be able to find the relationship for the delta U. And let's start state number 1. So state 1 is at 700 kilopascals. So if you look here in the pressure table at 700, okay, and I know that I'm at 15 degrees Celsius. So because the saturated temperature is 161 and my temperature is smaller than Tsat, then I know this is a compressed fluid. rule is my pressure greater or smaller than 5 megapascals? It is smaller, right? My pressure is 700 or 0.7 megapascals. And therefore, what I can do is I can approximate the properties to that of the saturated liquid in the temperature table, okay? You don't need to memorize this. If you go to the compressed fluid table, you'll see that it does not start until the pressure is significant, okay? It's going to start at 5 megapascals. Before then, you don't need to worry. So I can't use this table. Instead, I need to use the temperature table, this one here. I need to go to the 15 Celsius, okay? And this is where I'm going to grab all the properties for this state 1. So saturated liquid, saturated liquid, saturated liquid, saturated liquid. Okay, this is where I'm grabbing all properties for state number 1. They're all here. State number 2. State number 2. State number 2, we know 2 things about state number 2. Actually, for now we only know one thing. We know the volume is 0.5 and we know the temperature, the pressure is 700. But I can find out specific volume, right? Because that's the property that it interests me. Into that, for that I need to get the 2.5 and divide by the mass, which is 5 kilograms. So 0.5 divided by 5 kilograms, meters cubed divided by 5 kilograms gives me 0.1 meters cubed per kilogram. And with these 2 properties, now I'm going to go to the 700 again. So let's go to another table of 700. And I can check whether the 0.1 falls up, the 0.1 falls between these 2 fellas here, right? And it does, right? It's smaller than this guy, yet bigger than this one. So we can conclude it's a saturated mixture. And I can also calculate the specific volume, sorry, the quality, right? The quality using the specific volume. For that, all you need to do is relate to the property that I have and the properties that were given on the property table. And that tells me that this is 36.4. So there's 36.4% steam on this mixture and the rest is liquid. So if I want to know the internal energy, all I need to do is relate these 3 guys here. I can do that quickly. The internal energy 2 will be 6,962. 3 plus 36.4% times the difference, which is 1875.6. So therefore, internal energy 2 is about 1379 kilojoules per kilograms. Okay, beautiful. Last but not least, the third one. The third one has the same specific volume and is a saturated vapor. So what I need to do here is I need to look for a saturated vapor that is 0.1. That is my task here. So this is 0.2, 0.2, 0.17. I need to go to 0.1. And 0.1 is going to fall between these 2 guys here, right? Between the 0.11 and the 0.099. So that means that my pressure on state 3 is between 750 and 2000. And this also means that my internal energy, because it's a saturated vapor, is between 2596 and 2599. So what we need to do here is a quick interpolation. We know the specific volume, and it has to be between the 0.1134 and the 0.099587. And the one we're looking for is the 0.1. And here I'm going to grab pressure. And the only reason why I'm grabbing pressure is because it's one of the things we need to find out that we're being asked to find out is P3. Right? P3. And we know it's going to be between 750 kilopascals and 2000 kilopascals. So this turns out to be, if you do the interpolation, 1992.5, and that's kilopascals. And that, by the way, is one of the answers we're after. And on this side here, I forgot to put these values. This is 2596.6. 0.7, and this is 2599.1. So, not a lot of margin here to change, but what we get out of this is that this is 2599.0. Okay, and that will be our U3. Okay, now that I have all that, I can start calculating some things. For instance, what is the work total? Work total, like we said, is work 1 to 2 plus work 2 to 3, but 2 to 3 is nil because there's no change in volume, so this is just 1 to 2. How do I calculate 1 to 2? So I know state 2, I have everything I need. Okay, so work from 1 to 2 will just be the integral P dV. Pressure is constant, so that's just going to come out of the integral, and then I just have delta V. Delta V is going to be V2 minus V1. V2 is 0.1, and V1 is a saturated liquid, so therefore this guy here, 0.001001. So therefore, work from 1 to 2 is, what did I get? $69.3, and that is kilojoules per kilograms. Okay, so if I grab this value here and it come down here, then I can say that my work total equals, and I can multiply this by 5 kilograms, which is the amount of mass we have, and that's going to give me 346.5 kilojoules. Okay, that is one of the things we were after.